So hello everyone. In the previous session, we have been discussing about the bag of words. The problem that we are solving is if we have a document, we have seen these terms that are used in natural language processing like document, corpus, term, and things like that, then document, and we want to convert into a vector. The technique that we saw was bag of words. Okay, I think that technique was pretty clear. Now what we'll do is there is also some pre-processing done. If you see the problem with bag of words, so the problem with bag of words was I can, for example, it is this is a car, and you know that the word this will occur in more sentences or more documents it will occur. So there should be some pre-processing done so that we do not give some weight to these words like this is or some words which do not carry a meaning or something like that, which carries a meaning but they carry a meaning with context or something, so they don't have the individual meaning like conjunctions and these stuff. Okay, so better we should remove those words. So there are some steps involved which we call as text pre-processing. This also comes in pre-processing though, but there are some certain things that we have to do so that we do not give unnecessary weightage to the words that are not so important. And there are in English there are way more words that are not important, because we have seen a lot of sentences yesterday, and you can see that these words frequently occur is and these words do occur in that. We have seen, let's suppose we saw sentences like I love cats and dogs. Okay, I may not be like having much meaning, or dogs are loyal pets. R is not having much meaning. Okay, and some of these words they're called as stop words. So what are stop words? So stop words are the words which usually do not carry like much significant meaning, so they are not that significant, and and we have to remove the stop words. So we usually remove these stop words. So stop word removal is the technique of text pre-processing. So stop word removal, this is a technique. So stop word removal is a text pre-processing technique. Okay, it filter out the common words. These are common words like is a common word, as a common word, and they are not much significance. Okay, when you analyze the data of, is, the, and, etc., the words like these, they do not include, they do not have any significance, and they have significance, but they don't have much significance. And the second thing is that they occur very frequently in all the documents. Okay, so that's the rationale behind that. So we remove these words because they appear frequently and they contribute very little to the overall meaning. Okay, why do we remove these stop words? Because they are very frequent in every document. So whatever document you take, they are frequent in that. And the second thing is they carry very little meaning. So they carry very little meaning, like in the context. Okay, and they contribute very little. So that's why it's better to remove these words. Okay, let's consider some sentence and we'll see what to do. Let's suppose the quick brown fox jumps over a lazy dog. The quick brown fox jumps over a lazy dog. This is a sentence. If you see it, so we can remove the words like this. So we can remove we can remove this we can remove, maybe these are the words, and for also we can remove this. If there is for, there is not this fox. So these are the words we can remove. Okay, and over also can be removed. So now quick, brown, fox, jumps, lazy dogs, these are meaningful. They provide some context, and they contribute some significant meaning to the overall context. Okay, but these words, if you see the and this over, they do not carry that much significance. Okay, and they are more frequent. If you write some other sentence, if you see a document, these words will appear more. So that's why we remove these words. So what is the benefit of this? The first thing is we'll reduce dimensionality. We'll reduce dimensionality. Now you saw yesterday that when we were creating bag of words, in that the dimensionality of the vector was the total length of the vocabulary. So you are considering vocabulary. Now in the vocabulary itself, what are you doing? You are removing these words, so it will reduce dimensionality. So what will happen if you reduce dimensionality? So overall efficiency will increase. So by the help of this, efficiency of the algorithms will increase, because now you have a less dimensional vector. So you reduce the dimensions, and then whenever you feed the algorithm, it will take a smaller vector now into as an input, and smaller vector contains the same information that was there in the bigger vector, because you just remove the words which we call stop words, which have very less which contribute very less meaning towards that sentence in a particular context, and they are very frequent. And second thing is we also reduce noise. So what is the meaning of noise? Basically these words also do not provide any useful information. So noise is anything that do not provide any useful information, so that's called as noise. So noise, if you like, in terms of, let's suppose, the literal meaning of the word noise, it means anything which does not convey anything. Let's suppose I'm talking, if there is some noise coming. So what I mean by noise is, so there is no information there. So in the similar context, in our document context, if you have noise in a document, so what does that mean? So that means there is some information with, there is some text which does not contain any information. That's noise. So here these words, the is or words like that, they do not contain any information. Okay, that's why they are considered as noise. So these are the benefits of stop word removal. So these are the benefits. So this is first the technique, like if you process the data. Now you have bag of words. You saw that, oh, I want to create bag of words, but it's better if I could remove some of these words which do not contribute much meaning to the sentence, or which do not contribute much meaning to the document. So it's better to remove those. So that's why we use stop word removal techniques. Okay. And then there are also limitations. So sometimes you can lose the context. Okay, if you just have rule based on some things like that, and if you remove things, so you lose context. Okay, and let's suppose you consider one word to be of less significance, but in some other domain, let's suppose if you have words like stock, okay, or if you have words like buy, maybe you consider them, these are stop words, because maybe they'll occur at many emails, and then you see that these have some significant meaning in terms of, let's suppose, in finance. If your documents are financial, so it is better not to remove these words. So what are some disadvantages or limitations? So I'll also give those limitations. Everything will have that, but the point is that when you do these techniques, heuristically you see how they perform overall. Okay, and in some tasks they perform really good. So first thing is it loss of context. So loss of context is sometimes many words which may not carry the meaning, but when used in context, they'll carry the meaning. But in stop word removal, you have to be careful which words are am I removing. Okay. Then I said there are domain specific words. You can also remove that. So when you remove some words, but in a particular domain, they may have a meaning. And I was like very surprised when I saw this. Not is also a stop word, because I was checking what are the stop words present in this. There is a library called as NLTK. So in that they have a bunch of stop words defined, and they have defined stop words like before, have, few, but, yours, and I also saw not is also there. Okay, and if you remove not, it changes the whole sentence. I let's suppose we have a positive sentence. I like this food. I do not like this food. If you remove this do not, I do like this thing. I do not like this food. So it completely changes the meaning. So you have to be very careful. Okay. So let me show you the stop words that are present there in that library, so that you also get to know these stop words. Okay. So this is that library. So if you see over here, so this is NTLK, and then you see this, I'm importing from that stop words. So then I'm downloading the stop words, and stop words I'm getting as a set, and then I'm printing it. If you see the stop words over here, so you can see these are the stop words. Okay, few, and then off, you have ULT, before, itself, MA, home, and they have defined a lot of stop words. You can see over here, and not is also one of them. And you can see were not, shall not, or something, should not. Okay, own, now, one, have, yours. So the all of these are stop words. There are a lot of stop words in here, so we usually remove these stop words, but be careful. So you have to be you have to see what is the context of this. So if there is a domain specific context, do not remove these things. If you are having this not has a significance, let's suppose you are watching reviews and this restaurant is not good. Not good means that there you should not remove the not. Okay, that's what I wanted to convey. So sometimes you might feel that this word is not important, but in certain contexts it may be important. That's what I said in the limitations. If you can see, I wrote in the limitations itself. So in the limitations I wrote that sometimes there is this loss of context, and also I said in particular domain one word will have meaning and other word will not have meaning in that domain. So it is better you be very careful with this. So this is the first technique that we saw in pre-processing. So when we have a text, try to remove the stop words. Try to remove the words which do not carry much meaning or does not contribute meaning to a particular context. Okay, then there is something called as stemming. So stemming. What is stemming? So stemming is a text normalization technique. Okay, so what you have is basically let's suppose you have a word. In the previous example I said that this bag of words have a problem. If there are words like run and ran, they have the same root word run. Or if you see uh, beautiful and beautifully, So both of these words, so beautiful and beautifully, both of these words, if you see it, they have the same stem word. That's why it's called stemming. So for these words, we write the root words instead of that. So stemming is the technique which normalizes the words. Okay, so it reduces the word to their root. So this technique is a normalization technique. Normalization. So what it does, so it reduces the words to their base, or to their root form. So it reduces the words to their base or root form. Okay. So how does stemming work? So usually you add these prefixes or suffixes to the words. Okay, and you remove those prefixes or suffixes and you leave the stem behind. And there are a lot of algorithms, like there is a Porter stemmer and there is snowball stemmer, and I won't go into details of these. These are separate algorithms for these. Okay, they basically use series of rules and steps so that the common suffixes and some common endings, they are just removed out of the word. Let's suppose you have running. You have these words running, and you have a word run, you have a word like, let's suppose ran or something, maybe the words like this. So they'll just cut down this much and they'll get in the root words. Running and run basically is similar for it. Okay, even ran, so they'll just use some certain rules. So I said there are different algorithms for this stemming, so we don't need to discuss the details. These algorithms basically are a set of rules. Okay, they are just set of rules. So there is Porter's stemming, and if I remember correctly, then there is snowball stemming. So if you're interested, you can just look how these algorithms work. So they have a set of rules. They just try to just remove the prefixes, remove the suffixes, basically, which are called affixes. They try to remove these so that you can leave the root word behind. Okay, so what are the benefit? Again, you can so the benefit basically is you get some context out of this. The bag of words had the problem. So if there is word run and running, so it will be considered two words. Now the thing is, if you just perform stemming first, so this run and running will be converted to run, and because they basically mean the same thing, so that's what they provide the benefit over there. Okay, so they will improve your information retrieval if you say like that. Is everybody understand the things? So again, giving the big picture, the big picture was we have some documents and we want to convert them into vectors, and we saw a technique called as bag of words. Then we saw some problems with that. Now we are trying to see, can we somehow process the text first before applying bag of words? Can we apply some pre-processing technique so that we get the maximum out of our bag of words technique? So the first technique that we saw is stop word removal. So we can remove these stop words, the words which do not carry much meaning, or which are not that significant, or which are frequent in every document. So we can remove these words. That's called a stop word removal. And then the second thing that we saw is stemming. The stemming basically means, so words come from a root or a stem or a base word. So if there are words like that, we try to convert them into that base form again. Like I gave an example of run, ran, or beautiful, beautifully. So you'll just remove these affixes, basically prefixes or suffixes. You remove these from the words, leaving behind the stem word. Okay, and I told you what are these algorithms. They basically are some algorithms, some set of rules which will tell how to remove these suffixes and prefixes from the words. So there are two famous algorithms for stemming. One is called as Porter's stemming, and this is called snowball stemming. Okay, and this was proposed by Martin Porter. Okay, so and you can, if you are interested, you can just look at the details of these. And then there are also limitations to this. So everything has a limitation. So some problem you can overstem a thing. Let's suppose you have a word universe and university, and maybe your algorithm may consider this university and universe as the same thing. Okay, and what will do it? It'll maybe cut down the words and it will convert both of them into universe. Let's suppose you have university and universe, and let's suppose your algorithm is such that it will cut down this word. It will cut down the words till here. It will cut down the city of this. It will cut down maybe SE of this, and you are left with this. If you see universe or something. Okay, so these are some limitations, and you have to be careful in that. But stemming provides a good way. So if you have these words like run, ran, runner, and things like that, so you can stem out the words. You can just get the root word, base word. But be careful about these things. So if these things are removed, and if sometimes if they are removed, so that so these techniques have much benefit than the limitations they have. So anyways, sometimes most of the times we'll use them anyways, because if they even have some limitations, have some disadvantage, but their benefits are more than limitations. Okay, maybe it does some harm to the text, but it provides much more benefit than that. That's why you generally use these techniques. So this is second. The first thing that we saw is, so I'll just keep a track of the things that I told you. The first thing is stop word removal, and the second thing was stemming. And before stemming, even everything should be converted to lowercase also. That I told in the previous session also, so that everything is uniform. So if there is a word run and if there is a word run, these words should not be treated differently. So it is better to convert them either to lowercase or to uppercase. So howsoever you want to do it. So now then there is another technique called as lemmatization. Lemmatization. So these are just pre-processing techniques. So whenever you apply some bag of words, some vectorization technique by the help of which you convert a document into a vector. Before that, pre-process text in certain ways. So what is lemmatization? Lemmatization basically is how do you break the text, okay? And it again is like a sophisticated technique. It first breaks the text, then identifies parts of speech and tags each of the things, okay? And then determines, okay, what part should not be removed and things like that. So in nutshell, I'll say that let's suppose you have New York. You don't want to consider this as separate word, because this usually is considered a single word, okay? And sometimes there are multiple, like suppose 3 words, and which carry a significant meaning. So if this is in a news article, let's suppose, so some headline is there, so there was an elephant caught in New York, something like this. Okay, now you see that if you tokenize this, if you break down the individual words, if you see it, so new will be a separate word and York will be a separate word, okay? And but what lemmatization does is it will consider this as a single word, okay? There are again techniques involved in that. So the first is that you do tokenization. You break down the sentence into these tokens. Then there is part of speech tagging. So I'll just write the steps involved, usual steps. So usual steps involved. So the first thing is tokenization. I just want you to know these, because more of these jobs you won't do yourself, but because there are algorithm, you can just import that thing and you can use them. But underneath the hood, you should know what is happening. So first thing is tokenization. So what is the meaning of tokenization? Whole the sentence or whole the document will be broken down into the individual words or tokens. And then second is called as part of speech tagging. So each word is assigned a part of speech. Let's suppose noun, verb, adjective, based on its context. So howsoever it's used in the sentence, so based on that, each word of the sentence or each token of the sentence is assigned a part of speech. Then third thing is we do morphological analysis. Morphological analysis. Okay, in this, the morphological structure of each word is analyzed. Okay, so basically we call it, this is done to determine the lemma. Let's consider this considers various because we have considered part of speech and then endings and irregular forms, all of these, and we do the analysis. How basically the word morphology basically means how is the word, what is the forming of the word, what is the, let's suppose you are using it in a certain context and you do the analysis of each word and you make a sort of table for that. Okay, and then you have this lemma lookup. So I don't want you to even understand the whole of these techniques because these are sophisticated techniques, but I want you to know what is going under the hood. So in lemma lookup, you now retrieve the information because you have a predefined vocabulary for that. You have a predefined vocabulary or dictionary based on the words and parts of speech. So now first you did tokenization, you did parts of speech tagging, then you did some morphological analysis, and you came up with a lemma. So we call it, so when you do this analysis, you'll come up with a lemma, and then you will do lemma lookup. So what is lemma lookup? So you have already created some vocabulary and dictionaries, so which contains based on the words and parts of speech, and then by using this lemma, you just retrieve that information from the lookup table. And these are again rule-based algorithms. So they are again rule-based. So they have these if-else statements. Basically, wherever we have these rules, so we call them rule-based. So they are rule-based algorithms. That means they use a set of predefined rules, each for part of speech, for this morphological patterns and these things. That's why they are maintaining this lemma lookup table. So first tokenize, then tag this part of speech, then do the morphological analysis to come up with a lemma. Now you have this lemma lookup tables, and you'll just see from these tables, so how to basically retrieve the information from that. Okay. So consider like a word, the boy was running and saw a group of runners. Okay, so if I see the boy was running and saw a group of runners, this is the sentence. So when you apply lemmatization on it, so it will be like this: the boy be run and see a group of runner. So it will be converted like this. So you saw this was converted into be over here. Okay, and then this saw was converted into see, and this runners were converted into runner. So this is runners, group of runners. So group of it is converted like this. Okay, and running was converted into run. This running was converted into run. So what happened basically is, so it first tokenized the whole statement, then tagged it with part of speech, then based on the word it did morphological analysis to get the lemma, and from the lemma it has a lookup table, basically lookup things, and it looked up for each word and it converted it into that. So that was like the boy is like boy, but was converted to be, running was converted into run, and is like that, saw was converted to see. Again, as their group is there, off is there, running was runners were converted into runner. Okay, that's how the lemmatization is done. So it basically improves the semantic understanding. Okay, by reducing the words to their lemma, and these are called lemma. These reduced words are called lemma. Okay, the C is a lemma, B is a lemma, runner is a lemma. Okay, and then it improves your interpretability. Now, for let's suppose this sentence also carries the same meaning which this file here, but this is grammatically correct sentence. But in NLP, we usually don't care about the grammar. Okay, we want to get an embedding so that it machine understands it. But if you have to speak, maybe if I speak this in front of people, they'll be easily able to understand this. But this sentence is grammatically incorrect. Okay, but the point here is to make the machines understand, and we don't care about the grammar. That's why we just removed some words and we try to get into a format so that it improves the semantic understanding. Okay, and because we are reducing the words to their lemma. So how many of you understood these techniques? So I just told you some pre-processing techniques. Again, going back, so here we saw that first, if you have a document, convert that into either lowercase and uppercase, then do the stop word removal, remove the stop words. So by stop words, I mean the words which contribute very less meaning or which are very frequent in the document. Then we do the stemming, get the words into their stem format, and then we saw one more technique, that is lemmatization. Okay, so lemmatization basically was to this is the steps involved, and again these are rule based algorithms. Is everything clear? Any questions? Now that you saw these techniques, again I told you that if you remove the stop words, then there is a problem that sometimes you can remove also not. So for example, you had a word like I like this restaurant, I do not like this restaurant. Maybe you will remove the not if you remove the stop words. And in order to do that, what we have something called as n-grams. Please focus over here so that you understand these things very well, because these are very basic techniques, and these, if you do some natural language processing, these will occur frequently. That's why I'm saying you should have your fundamentals very much clear, and after that you will like basically build your foundation based on these. Build your whatever the things that you will be doing, build advanced concepts, and that's the foundation you will have. If you are really clear with these things, then your other concepts will be also good. Okay, so that's why I'm telling you to focus more over here, ask questions. Now we'll see what n-grams are there. So if we have this not as a stop word, so let me write a sentence. Let's say I have a document 1 which contains food is tasty. So this is my sentence. And document 2 contains food is not tasty. Is not tasty. So in this, if you see that, if I had to give these reviews as sentiment, so is this review positive or negative? So this can be treated as positive review, and this is as negative review. But I said there is a technique called as stop word removal. So if you just use the stop word removal, it'll remove this not also. Okay, it'll remove maybe is, it'll also remove this not. So food tasty, both the reviews became the same. Okay, so how to overcome that? So now what we have is this. So you will tokenize it as a different format. So in natural language processing, we do not tokenize by just seeing the word. We'll take particular like characters or sequences we'll take. So usually if I take unigram, so unigram basically means taking one word at a time. So unigrams. So what is a unigram? So unigram is a single item or a token from text. So in the context of text analysis, unigram are typically single words, okay, or single characters, let's suppose. So food over here, this is a unigram. So if I tokenize like this, so this I am saying each of this is a unigram because I am taking a single word. If I take a single letter also, that's also unigram. Okay. Then we have bigrams. So bigrams basically tell me, so I am taking two words at a time. So when I'm constructing the vocabulary now, I won't consider just one word at a time. So when I was in the bag of words, I was considering a vocabulary first. So in the vocabulary, it will be food, is, tasty, okay, and not. This is the vocabulary. So if I remove the stop words, so is will be removed, not will be removed, okay, and then only two words will be in the vocabulary based on these documents, based on this corpus. But what I want to do now is by using the bigrams. So I'll use two words at a time. Let's suppose food is a one word. So this food is will be used as one term in the vocabulary. Then maybe here tasty, and if you see food is and not tasty will be another word in the basically another term in that vocabulary. Now you can see that you cannot remove. So if you apply the stop word removal now, so you will not remove this not, because this not tasty is considered as one single word now, or one single term now. So because you are using two sequence of two consecutive items for tokenization. Okay, even the quick brown fox jumps for a lazy dog. For in that, the quick brown fox and something like that. Even you sometimes use rolling windows also. It's not like you will just use this and then is this. Sometimes you roll the windows. I'll tell you what I mean by rolling windows. Let's suppose I have the quick brown fox jumps over a lazy dog. So one technique is that if you use bigrams, so you can use this as one word, this as one word, this as one word, this as one word, and this as one word. So another technique which is called as rolling window technique. So in that you roll the window basically. So what you do is you'll first use this as a bigram, okay, then you'll use this as bigram, then you'll use this as bigram. Basically use previous one and the next one. Okay, you just slide the window. So if you see, I'm just sliding the window. Why it's called sliding window? Because first your window was this, then you slided the window over here. Okay, so you're just sliding the window by just one word. That's why the quick brown fox jumps over the lazy dog, and something like this. And each of these will be one token. Okay, so this the quick is a token, quick brown is another token. Okay, this is how you tokenize the things. And similarly you can have trigrams, quadgrams, and beyond. Okay, they are called similarly n-grams. Okay, I told you the rationale behind them. So the problem is that you generalize it, so that for example for stop word removal, or because some certain words have a contextual meaning. Okay, so you try to capture that context. So let's suppose you have this fox, you have this jumps. So jumps, if you take fox with it, so fox jumps has a particular meaning. Okay, some foxes jump, it has a particular context. So it is better to have these tokenization in bigrams. Okay, what are the practical examples, like when you use it for the language modeling? So in that you basically use it, you usually use trigrams for the language modeling, because probability of three words coming together, like same three words, is very less. That's why you say that, let's suppose if you see this brown fox and jumps together, so you can easily understand the context what is happening. So usually these things are used. So that's why even now if you see how ChatGPT even predicts the next word. Okay, because it also sees the context. What is the context previously I saw, and then what is the probability of next word detecting. That's why when you type something in the ChatGPT, it gives answer like after one word generates one word, then generates next, then generates third word, and basically what it does is it basically takes the previous context into consideration. So whatever context it has done, it has generated so far, and then it generates the next word. It's called next word prediction. Okay, and by that it generates the whole sentence. And you might have seen that ChatGPT does not give you sentence in the flow, and it does not give you directly one sentence. It gives you word per word. Okay, that's what basically context is very important in language. So if I speak something, so previous context and what is coming next is very important. That's why we use these n-grams, bigrams, so that we do not miss the contextual information. Is it clear?
Yes, sir.
Okay, so these were some pre-processing techniques that we use for the text. Like we saw one technique, that is bag of words, and before even bag of words you can use these techniques. And why did I introduce the technique first? Because I'll tell you the limitations and then how to overcome these limitations. Now we'll go on to some advanced techniques of converting a document into a vector. By document, I mean an email or a review or maybe some medical document, whichever it is, because I will have given terminologies. And then whole documents is called a corpus. The technique that we'll study now is called as TF-IDF. Okay, what is this TF-IDF? So if I expand it, it's called as term frequency, comma inverse document frequency. Like really powerful technique. So when you convert a document into this TF-IDF vector, so it's performed better than bag of words. So whatever we had, whatever we have done in bag of words, so if you just give this TF-IDF, so it will give you better results. So all of these things are called sometimes embedding, sometimes vectorization. Or you might have if you read papers, there you will see this is the embedding of this vector, and sometimes you will feel this is the vector corresponding to this document. And do not get confused there. So vectors, embedding, they are sometimes used interchangeably. So again, to bring you back at the point, so what we had, we basically were converting. We had some emails, and for those emails we have to see whether it is spam or not spam, basically ham emails. So that was our task at hand. So then the first problem we got struck with, that this emails are in English, so they are in pure English, and now our algorithm would not understand English, so it will basically understand the numbers. So to convert this text into this vectors, now we were seeing these techniques. The first technique that we saw was bag of words, and after the bag of words, we saw that before even applying any technique, make sure that you use the stop word removal, you use this lemmatization, you use stemming, and the other techniques that we saw just now. Okay, now I said that bag of words has its limitations, and to overcome the limitations, people came up with other techniques. The first technique, the second technique we'll see is TF-IDF, term frequency inverse document frequency. Okay, now we'll see each of this, what this term frequency is, what is this inverse document frequency, and then we'll put them together and we'll see how to form a vector. First, I'll introduce you what is a term frequency. Okay, by the name, when it says it has to do something with the frequency, something with the number of occurrences. Okay, let's suppose I'll take some documents D1, D2, D3, D4. These are my documents. The documents can be reviews, these can be emails, whatever you have. Okay, now in each document I'll have some words or some tokens I can have. So let's suppose I'll have word 1 here, word 2, word 1 again, word 3, word 5, word 1, word 6, word 9, word 11, word 15. Okay, just give me a minute to write this. Let's suppose I have some documents like this in which there are words, and there can be, in practical, there can be more words than this. And now what is the meaning of this term frequency? So how I will write this term frequency? So I'll write this term frequency of a word, let's suppose word I, in a document J. This is how I'll write it. So this is the symbol that I'll be using. So term frequency of a word I in a document J. So now I'll define how I'll define it. So let's suppose if I take WI word. So if I take this word W1, and I'll now count the number of occurrences it has in the document. Okay, so I'll count the number of occurrences this has in the document. That's W1. How many times it occurs? It occurs 2 times. So okay, so the frequency basically is 2 in this document. And what's the number of total words? Total words number is 1, 2, 3, 4, and 5. So total words is 5. 2 by 5. So this is how I basically convert this. So if you ask me what is term frequency, so term frequency of a word or a term, this is called as term or one word. So it is basically the occurrence, how many times has it occurred in the document. Okay, that's known as term frequency. So if you take this word W1, so I can write term frequency of W1 in document D1, that is 2 by 5. Okay, if I say term frequency of word W1 in document D2, that is 1 by 5. Okay, because I have 5 words over here. Term frequency of this word W1 in document 3, I think, is 0. If you see, it's just like a probability score. So what is the probability that you will see the word in the whole document? Okay, so if your document contains 100 words, among these 100 words, so let's suppose the word occurs 5 times, so that is the probability is 5 by 10. That's what it's called as term frequency. So if you have to compute term frequency, you take that term, see the number of occurrences it has in the document, divided by the total number of words in that document. That is how this term frequency is counted. So term frequency basically it's a measure of how frequently a term occurs in a given document. Okay, the more times a term appears in a document, the higher the TF value is. Okay, so when is TF value higher? So if this W occurs more frequent in the document, so this indicates that this may be more relevant, because let's suppose if you see a document which is filled with the words like stock market, and if you see stock market everywhere, and you can see that this somehow has to do with something with the finances. And if there is some, let's suppose some word like diagnosis everywhere, then you can see that diagnosis is a particular word to the medical, so maybe this document is a medical document. That's why we see we compute this term frequency first. So again, to come up, term frequency measures how frequently a term occurs in a given document. The more times a term appears in the document, the higher the TF value is. Okay, it indicates that term may be more important to that relevant document. Okay, then we have the other thing is called as inverse document frequency. So then we have the second term as inverse document frequency. Okay, what is this inverse document frequency? So inverse document frequency, it measures, first I'll tell you what does it measure. It measures the rarity of the word. It measures if a word is very rare. Okay, if you come across the entire corpus of the document, okay, if a word is very rare and it's particular to that document only, okay, then it will assign it some value. So it will see if a word is rare. Let's suppose you are looking from a huge document, so you have a corpus of huge documents, and there you want to label medical documents separately. So like for example, gastric cancer. So words like this will occur very rarely in documents. So if you have words like this, so this highly says you that is the medical document and something like that. So rare words sometimes convey you something. So if there is a word which is very rare, which is not there in all other documents, which is occurring but in certain documents, okay, that word is not, let's suppose if this the, it's very common, and it does not have significance, because if it's present in all the documents, that does not give you much information. But if there is a word which is very rare, it will tell you something about document. That's why we are interested in finding these rare words. So the inverse document frequency, basically this gives you the measure of how important or the how rare this term is across the whole corpus, across the whole collection of these documents. Okay, so how is it computed? So now as you see that we have these documents, so how to compute basically the inverse document frequency of a term. So here if you see that this TF takes two arguments. The first thing was word and document. So it was counted based on the document. So now you will see this IDF basically is counted for the term only. So how is this counted? So you can see if I take a term, like I can write IDF of 1, IDF of W1. So how is this converted? So you will see what is the total number of documents. So first you will see how many total documents are there in the corpus. Okay, and then you will see divided by n. So this small n is how many number of documents are there in which this T occurred. Okay, so if I write IDF of 1, so how many documents are there? There are 4 documents in total. Okay, so how many in how many documents has W1 occurred? So in this it has occurred here, it has occurred here, in 2 documents. So I'll write 4 by 2. So this is giving me 1 by 2 number. Okay, actually 2 number. So this is 2. So this is giving me 2, a number, particular number. So if that number is higher, it means this word is very rare. That's why it's called inverse document frequency. That you can see it clearly. Okay, a document frequency basically tells you how many document is present in. That's document frequency for a particular word. If I tell you what is the document frequency, what is document frequency, you can tell me that in how many documents does the word appear. So in here it was 2, but now it's called the inverse document frequency, because now you are inverting it. You are writing it 1 by something, okay, inverting it and seeing the total number of documents. So if I say what is the document frequency will be 2 by 4. That is 1 by 2, because that's how many times the word appeared and divided by total number of documents. That is the document frequency. So inverse document frequency is just inverse of this. So that's why I'm writing it over here. And if you see, we apply a log in this. So we'll apply log on this. So log of this. Okay. So this over here is called as IDF, inverse document frequency, for a particular term. Okay, so I'll write it maybe like this. So inverse document frequency of a term is equal to log of n divided by small n, or I can write df of this term t. So df of this term t basically means the number of occurrences, the number of documents that t occurs in and this is the total number of documents. The question here is, why should we apply log? Okay, why should we apply log? I'll come back to this answer, because first I'll just put these things together. So how to compute this TF-IDF now? So now we know what is term frequency. Now we know what is IDF. Okay, and we have this. So term frequency is the frequency of the term in a particular document. IDF basically is the inverse document frequency of term. So now in order to compute this TF-IDF, we multiply these two terms. So you just multiply them. Okay, now I'll tell you how to do it. You have a vocabulary. Okay, now you have this vocabulary with you. This will contain set of words. Now in the bag of words, what you did, you just, let's suppose this was our word 1, word 2, word 3, word 4, word 5, word 6, something like this. And then what you did, you just saw the occurrences. Now you not just put the frequency over here. So what you will basically do is, you will multiply this frequency with the inverse document frequency also. So again, see it over here. This tells you how frequent that word is in the document, and this tells you how rare that word is. Okay, and then you multiply both of these things together. And now you will put that entry over here. For W1 word, you will multiply it with frequency, and then you will see its inverse document frequency. How rare that word is in the document, how rare that word in the whole is in the whole corpus, and you will put that entry over here. So for W1, you will compute TF of W1 corresponding to D1. Let's suppose this is the representation of document 1, and then you will multiply it with by IDF of this W1. Okay, that will be the entry over here. And if you see the second entry, that will be TF of W2 in the document 1 multiplied by IDF of W2. Okay, and this will go on. This is how you will fill this vector. Again, this will be a d-dimensional vector based on the vocabulary, and D here I consider that this is the number of words in the vocabulary. Is it clear? Tell me if it is clear.
Yes, sir.
Yes, sir.
So now what is the significance of these? So here if you see this term frequency, so what term frequency tells you is that how frequently the word occurred. Okay, and the second thing is that IDF is how rare the word was. So how this works is basically it assigns value to the words which are more frequent and which are rare. Okay, so it assigns, so if you see this term frequency, this assigns some weight to frequently occurring words. Okay, and if you see this inverse document frequency, it tells you if a word is rare, it assigns the like higher value to the words which are really rare. And then I apply this log. Now I'll tell you why do I apply this log, because log is a monotonic function. So if you see it, so why I apply this log? So if this n by n, let's suppose nt, so I have this IDF of some term t, this is equal to n by nt, so log of this. So the maximum value that n by nt can take, if you see it, so this nt can be present in all the documents. So it can take the value of 1. Okay, so if you take it can, the value of n by nt is always less than equal to 1. Okay, do you agree? And it should be positive also. It is between basically, so it can be let's suppose in 0 documents or something. So if you see this n by nt, so this nt can be 0 also. So sometimes you will see people adding +1 over here also, so that not to get into that, because if the term is not in any document, so then you will have the problem, you will have division by 0. So it is better to have this n divided by nt plus 1. Okay, and now you will understand, most of the papers will have written the formula like this: IDF is n divided by nt plus 1. So why do they add this +1? Because sometimes a word is so rare it does not appear in any document, let's suppose. Okay, you have a big vocabulary, and that time then you see that this word does not, and you make that vocabulary based on some other corpus, and you see that this word is not in any document, so that you add this just +1 beforehand. Now if you see this n by nt plus 1, its value will be less than equal to 1. So now if you apply log on this, so log of n by nt, this will be greater than equal to 0. Okay, so this will be greater than equal to 0. This means, so if the number is, if this n by nt, so if this nt is going high, okay, if this nt is going high, so this number will become much lower. Let's suppose I'm telling like this, so this n divided by nt is there. So obviously one thing is that n should be also less than equal to nt, this small nt it is, or maybe greater than, so this nt should be less than equal to n. That means the number of occurrence in the documents, this is the total number of documents, this obviously should be less than equal to this. So that's why I can conclude that this 1 should be less than equal to n divided by nt, or I wrote that n by nt will always be greater than equal to 1. So that's why I can conclude this. I hope that everybody is following this much of maths. So this is really easy. So what I'm saying is the number of times this term is appearing in all the documents is nt, and this number of total documents. So if I just use the mathematics manipulation, I got this. So n by nt is greater than equal to 1. So if I apply log on this, so log of this term, log of n by nt will be greater than equal to 0. Okay, now I'll see the relation. So if I increase nt, let's suppose if I increase this nt, obviously this value will get decreased, so this value will be decreased. So if I increase nt, so n by nt will be increased. So if you increase this value, again you will apply log on to that value, and you will see log also it will also increase. So this value will also increase. Okay, so what I'm telling you basically is this. So if you do not apply the log, let's suppose you have this words like this. So you have a word is, it is in let's suppose out of 1000 documents, it's in all the documents. So let's suppose there's a word this is in 999 documents. So if you see a word, let's suppose like rhinoceros or something like this, some word, so it appears only maybe 1 times. So now if you have this n by nt and we have this log of n by nt, see the effect. So this n by nt, if you calculate this, so this will be equal to 1, this will be again 0.9, somewhere around that. So if you see this, so this will be 1 by 1000 if you have 1000 documents. Okay, now if you take log of this will be 0. Okay, if you take this will be again nearly something. Okay, now if you take log of 1 by 1000, okay, I'm using the natural log. So log, let's suppose I have this will be 1000 by 1, so 1000 divided by 1, so it will be I think 3 point something. So maybe I'll check log of 1000 to the base e. So this is equal to 3. This is the log base to the base 10, but I want log to the base e. Log 1000 to the base e. This is somewhat 6.9, I think. So because if I take log e to the base 1000, so this is equal to 6.9. Okay, so now you see this number. So here these numbers had a difference. So this number was nearly 0.00 or something like this. So if you see this term frequency multiplied by inverse document frequency, okay, so if this term is somewhere, this hardly will be around 1 to 20. So because term frequency, if you see how frequent is that term, so it will be around, let's suppose 0, it will be around 1, 2, or maybe let's suppose till 100 also. But if you see this IDF, okay, this can go to even 1000 or like this. So if a word is very rare, it can go to 1000. So if this term frequency, let's suppose the maximum value term frequency is 100, then if you multiply it with, let's suppose if you have a corpus of 10,000 documents, you will multiply it with 10,000. So obviously that word will get more value. If it is very rare, it will get way higher value, and it won't consider this term frequency into consideration. So this is some sort of imbalance if you see. So we want to bring both of them into the same scale. That is why we apply the log. So if I apply the log onto this 1000, you see this is 6.9. It comes in the same scale. Okay, it comes in the logarithmic scale. So that's one of the practical reasons why you use log of this. So how many of you understood the reason?
Yes, sir.
Yes, sir.
The reason being that we have term frequency and the inverse document frequency. If we used the inverse document frequency without the log, then that number will exceed way higher for rare numbers. So what will happen that it will assign the value only for rare numbers. It will not consider this term frequency into consideration, because maybe if it is very less, it will still assign it very high value. But here if I apply log, now you are bringing it to logarithmic scale, so then that number will be in a certain range. So because this term frequency cannot go, let's suppose if document is only having some 200 words, so term frequency will lie around 1 to 20 or something. So this IDF also want to be in the same range. The range, if it is similar, so we assign the same weights to this rarity and the frequency also. So that's why we apply the log. So when the paper was published, they did not give any mathematical reason, but this is one of the practical reasons. So also I have also read an explanation why the log is there. There is something called a Zipf's law. So a Zipf's law is a law basically which says if you just plot this number of words and the occurrences in document, you will see a graph like this. Like so words like is there almost in every document. Okay, this is the number of documents we have, and here we have the words. This is the count of the words in the document. So some words are like, most of these words, they are very high, like the, is, and these words are very frequent in document. And you will see some words are very rare, Let's suppose floxenosinylipilification is a word in English, so it will be very less. It will be very rare in documents. So this follows basically Zipf's law, and we'll see in the stats there is something called as power law distribution. I don't want to get into this argument though. Just remind me sometimes about the Zipf's law. I'll tell you. But I gave you the one of the reasons. So one of the reason is that to bring this IDF and term frequency on the same scale, we'll apply log onto this IDF. I hope this is clear. So now we have term frequency with us. We have inverse document frequency also. Now we multiply this. Now we want to create a vector that I also showed you how to create a vector. You compute for the vocabulary. What we will do? We will compute for each word. You will compute this TF-IDF and then have the values over here. I hope that this is clear. Can I conclude that this is clear?
Yes, sir.
Okay. Yes, sir. Now we'll see in a code. We'll write a code from scratch and we'll see how to basically implement this in code. Okay, we'll basically follow the same steps, and when you are doing these on yourself, I'll highly suggest you to write the code from the scratch. Do not import it from the libraries, and after once you got a grasp of these things, then you can just import these things from the libraries, and that will benefit you that time. But in the initial go, please try to code everything from scratch by writing your own code, and do not import the statements usually. Let's go to the code of this inverse document frequency. Okay, here is this. So if you see, we have a set of documents. So something happened. Just give me a minute. Okay. So if you see it over here, so I have again a corpus of documents. Okay, I have a corpus. So in this corpus, you have different sentences. Now what I want to do is I want to compute this TF-IDF. What is the step one? Step one is we'll compute the term frequencies. Okay, term frequencies corresponding to each document. That's what I'll be doing over here. That is my step one. So step one over here is tokenize the document and calculate the term frequency for each term related to each document. And that's why I have this TF, basically the dictionary. So in dictionary, it will have key value pairs. So it will be like this. So I'll have key and values. Okay, that means for each of the document, I'll have this document and I'll have corresponding for the corresponding term, I'll have its frequency TF. So now I again have another dictionary, total number of terms in the document. Okay, both of these are dictionaries because I have to look it up. So now what I'm doing is I am taking these documents, okay, and getting the document index. This is document 1, this is document 2, document 3, document 4, document 5, and document 6. Now I'm getting document index and the whole document. Basically, I'm getting this whole sentence, and correspondingly its index also, its index is 0. Now I'm tokenizing it. So I'm getting all the tokens. So here, if you see how I'm tokenizing it based on spaces. So I'll tokenize it by using unigrams. So that is one token, cat is one token, sat is one token, on is one token, mat is one token. Okay, so that's what I'm getting. Tokens basically tokenizes the whole sentence. So if you see it over here, the cat sat on the mat, these will be tokens. Now what I'll do is I'll take this total number of terms in document. So this is, and I'll index it with the document index. So this is my index. Okay, then what I'll store there is length of tokens. So this is what I'll store there. Okay, what is the length of tokens? So that I'll store. Basically total number of words in that document I'm storing. So this basically is the total number of words. So here I have two dictionaries. So one dictionary is this TF term frequency and one dictionary is total terms in a document. So this is like this. So this is having document number over here and number of terms. So basically number of words in the document. Okay, this is my, so this is my dictionary. So in this dictionary, I'll have document and its corresponding number of total words. For example, for the first document, so it will be 1, 2, 3, 4, 5, and 6. So it will be 1, 0, 6. Then it will be for the dog, it is 5. So it will be 1, 5. So these values will be stored in this total document, total terms in document. So then I have this 1, 2, 3, and 4. So this will be 2, 4, and so on. This is what gets stored in this total term in document. Then for each term in token, so what I'm doing is now I'm having this these tokens, because I have stored these tokens into this token. I have stored this the cat sat on the mat in tokens. So for each the term, what I'm doing is I am using this TF. If you see this term frequency, what I'm doing is I'm taking this term and corresponding document index and counting how many number of times this term occurred divided by length of tokens. So that's how I'm getting this length. So I'm basically storing this term corresponding to each document now. So let's suppose I have a term here, cat. So cat appeared only one time in this, or maybe that we can start with that. So that appeared 2 times. Okay, and there is over here and there is over here. So it appeared 2 times in this first document. So what I will do is I'll store this 2 divided by 5. That's what I'll store, term frequency. So I'll correspond to the term and the document index. I'll store this tokens count, that is 2, and length of document, that's 5. 2 by 5 I'll store in this TF. Okay, and this TF is again a dictionary. So this dictionary will correspond, okay, corresponding to the term and the document. So there will be this term and document, and it will basically have this count. Okay, it will be a document like this. So it will be, let's suppose it will, in the first it will have this term there and the document 1, a document 0 we call it, the and 0. So corresponding to that it will have 2 by 5 value stored in it. So this is how it will be filled. Is it clear? That's the first step. How do we compute the term frequency? Is it clear?
Yes, sir.
Okay, now for each word we'll compute the inverse document frequency. I hope this is clear. If this is not clear, please watch this video again, because we have also understood the theory. It will hardly take you a few minutes to understand. Then the second step is to calculate the IDF. Okay, now we are in the second step, calculate IDF. IDF is really easy to compute, and you have to just compute the total documents we have. This is the length of total documents, and then for each term in the term frequency, because you will have these terms in the term frequencies, you just see the like how many documents have, was it in, and then you compute this IDF. Okay, and it will be, again, this IDF will be a dictionary, and it will have term over here, and it will have number of occurrences. Okay, so that's what we have here, and then we'll compute this n by n. So term, let's suppose we have term there, the document is, let's suppose 10, and it occurred in 5 documents, so it will be 10 by 5. And then you will also apply log. That's why we applied log over here. That's why I said total documents divided by documents with that term. So that this is our IDF. Now I have to compute a vector out of this. So see, how do I compute the vector? That's the third step. So now I have TF with me, term frequency. Now I have also IDF with me. So IDF is inverse document frequency. Now I just need to compute the vectors. So this is TF-IDF vectors. I'll just have a list with me. So then now I'll have for document index in the range of, I'll take all the documents. Okay, then I have the how I compute TF-IDF vectors. First I'll create a vector of zeros. So there are all zeros over here filled with zeros. Then I'll see for the term in this TF, take the term, and also take the document. If document is in the if that there is a term in that if that term is in the document, so what you will do is you will just have that like take that term. Basically this is the term frequency, and consider that IDF, because we have these two lists, two dictionaries, TF and IDF. These are two dictionaries. So what you will do is you will just look up the dictionary for that particular term correspond to that document and multiply with it IDF, because we have these two dictionaries, TF and IDF. So you'll just multiply them. Okay, and then you will get a vector for each of the term, because that's how you are running this loop, and you will append this vector for each of these sentences, and then you will get the whole list of, because it will be a list of lists. So first list will contain the TF-IDF of first vector. So again, to simply tell you like this, so we have this W1. I'll just maybe close the code so that I can show it. So we had initialized it with 0. So we had this W1, W2, W3, W4, W5, something like this. So these are my words. So now what I'll do is, so for W1, I'll look for term frequency of W1 corresponding to document 1. So this, I have a lookup table for this. So I'll have that value multiplied by IDF of W1. So also I have a lookup table for this. So you multiply these things and put the value over here. Again, same for the word 2. Multiply these two things, put the word over here. Same thing for others, and fill it continuously. That's what the code is doing. So step 1 is compute the TF. Step 2 is compute the IDF. And step 3 is you just have to multiply these correspond to the document, and you will get these vectors of this. So if I now run this cell, so you can see I have also, this is my document 1 TF-IDF vector is like this. Okay, and document 2 TF-IDF vector is like this. Document 3, document 4, and correspondingly you can see this. I hope that this code was clear. Was this code clear to everyone?
Yes, sir.
Yes, sir.
Okay, now the state or technique that we have is called as Word2Vec. So even if this like TF-IDF, it has its own advantage. It has again disadvantage. It does not take semantic words. Let's suppose it does not take context into consideration. So let's suppose if you have a word delicious, tasty. So these are two different words for this TF-IDF. Okay, and it also has problem, but it actually performs better than this bag of words. Why? Because you also consider the rarity of the words, you also see the term frequency, and you make the embedding based on that. The best that we have today is, I think, Word2Vec. So it was proposed in 2013 in a paper by, the paper was from Google. So this was like really amazing paper. So, but the internal details of Word2Vec we'll probably see when we go into deep learning, because we train a network for this. But here I'll tell you how this Word2Vec works. Okay, this basically is really popular. Okay, and most of this is widely adopted because it is nearly state of the art. I haven't seen another paper which gives as much accuracy as this is. Okay, so what this basically does is, if you give it a word, so as even the name suggests, Word2Vec means it will take a word, it will convert it into a vector. Okay, so you will give it a word and it will be converted into a vector. Each word will be converted into a vector, not sparse vector, it will be a dense vector. So here, if we saw that CBOW, in that CBOW, not CBOW, if we saw bag of words, basically, if we saw bag of words, so in that bag of words, what we saw is that there was sparsity, because most of the words won't occur. So then you saw that, okay, with the whole vocabulary, most of these are zeros. But if you use this Word2Vector, what it does is, let's consider it's a black box. There is something happening within. So you give a word, it will give a vector, and this vector, let's suppose, is some 100-dimensional vector. So this vector will be densely packed. It will not, it'll contain most of the zeros. So zeros won't be there actually. So it will be a dense vector. It won't be a sparse vector. By sparsity, I mean that, so in the CBOW you have vector like this, 0, 0, 1, some 2, some 0, and even if you see in TF-IDF, also the same thing was there. So the thing that was there also, there was sparsity in the vector. There were a lot of zeros in that, because many of the terms were not in the document itself. That's why we cannot, like, term frequency was 0. Okay, so then we had these zeros most of the times. But what this Word2Vec does it, this takes a vector and gives you a densely packed vector. And what is so important about this, like, this is really, like, really beautiful, I'll say beautiful algorithm even. So what happens there is, let's suppose you have an embedding for a word man. Okay, and then you have an embedding for a word woman. Okay, let's suppose if you see in the 2D plane, man is over here. Okay, woman might be, like, let's suppose the embedding is right here. So again, if you see the embedding of king, it will be somewhat here, and if you see queen, it will be somewhere here. So if it is man, this is woman, this is king, this is queen, because it respects relations. So this Word2Vec, it respects. So the embedding of the word man and woman, let's suppose that vector has this direction, and if you see this king and queen, so this vector will be parallel to this, because they share the same relation. Okay, same with the city and capitals it has. So you can write a blog or TensorFlow. There is a beautiful blog written on that. So again, if you have, let's suppose, cities, if you have, let's suppose, state and a city, let's suppose you have Kashmir and you will have Srinagar over here. Okay, and similarly, if you, let's suppose, have some other city, also some other state, and its corresponding city, it will have the same relation. And one more beautiful thing that was astonishing, so when I saw it first, so if you have king, you will have some embedding, you will have some vector representation. Okay, you will have some numbers over here. Okay, then if you subtract man from it, so man will have basically some vector representation. Then if you add queen to it, queen will have some vector representation over here. So this is king's vector representation, this is man representation, this is queen. It will give you woman. Like, isn't it beautiful? You see how it's capturing the relations. So you had king, you had an embedding of the king. Okay, this is a vector. Then you had a embedding of the vector man. Then you had a queen. So what you did actually is, you just said king minus man plus queen. It gave you woman. Or maybe other way around also. So if you just switch these sentences, so that's how it gave. The embedding were so closer. So if there is king, and if there is, let's suppose, some emperor, these will be really close in the embedding. So if you have delicious and if you have tasty, okay, these will have close embeddings. So when you use these Word2Vec, so when you use this, like, let's suppose this is a black box, if you use these words, so they'll get close embedding. That's actually what we wanted. So this is basically based on deep learning. So we'll see the internals of this algorithm once we cover the deep learning. So this is the high general overview of this. So it takes a word, not just a sentence, it will take whole word and give a vector corresponding to that. So that's why it's called Word2Vec, and you have sentence to vector also. So Word2Vec basically will take a word and it will give you corresponding vector to that. Okay, and how does it do it? It basically respect the context. So there are two famous implementations. I'll just give you those implementations. Like that, there is implementation called as CBOW. This is called as continuous bag of words. And there's another implementation called as skipgrams. Both of these maybe we'll see when we are in the deep learning. We'll see how to implement the CBOW. So what it does basically is, so it will have some words will be there. So there is a king and a queen. A queen. So sometimes in this it'll try to miss out this, and it'll see the previous context and next context and try to see try to predict the middle word in this. Okay, it sees the context basically, and based on the context it will try to predict the word. And the beautiful thing here is, for each word we'll have an embedding. It's not that for vector we'll have an embedding. For each word we'll have an embedding. So what we do is, we'll take a corpus. So usually what we do, we'll take corpus and we'll take this CBOW and skipgrams, we'll train this on the corpus. Okay, and we'll train the algorithm based on this corpus, and then we'll give this algorithm, and let's suppose a word, and now it will give embedding of the word. Embedding can be 100 dimension, 200 dimension, 300 dimension. Okay, and that corpus can be your own corpus, or you can use a lot of documents from the web and scrap the web and learn the embeddings. Even Google has had a corpus of Google News, so they trained this Word2Vec on this Google News. And now if you give any word to that pre-trained model, so it will give you basically vector representation and embedding. Okay, so these are like some important things I wanted to tell you about Word2Vec. So Word2Vec basically is state-of-the-art algorithm right now. So if you give it some word, it will give corresponding embedding to that. But this model has to be trained first on the corpus. So you give it a lot of corpus and you train the model, and after that you give the word to the trained model and it will give you the embeddings. So let me show you. So there is a library called a GenSim. So let me show you that in the code also, so that you understand it really well. So see it over here. So let's suppose I'm importing this library over here. So this is the library, and then I'm having this corpus. So what I'll do is, I'll train this model. So this is my model, GenSim model.word2vec. Then I'm using this corpus. This vector size basically means, so when I train the model, what is the output size that I want. So if I give word, I want 100 dimensional vector for corresponding to each word. Okay, and then there are different, how many threads do I need. So threads, how many work, this is like threads for the workers. So you can read the documentation for this, but this is how you will train your Word2Vec model. Okay, by using the GenSim library, it will use this CBOW implementation or skipgram implementation. Okay, and then after that you can give this, you can train the model, and you can get this vector is equal model.v of, and get the fox. So basically this will give the vector representation. If I run this, so if I run this, you will get the vector representation of 100 dimensional vector representation. If you see it over here, so this is the 100 dimensional vector representation of fox, just trained on this. But you should have a really huge corpus so that it understands the meaning, it understands the context of these words, so as to get this. So again telling you the same thing. So basically we take a corpus, a huge set of document, then give it to the Word2Vec. So Word2Vec basically learns from it, and after that if you give a word, it will give you a, let's say, n dimensional vector. So I told you about the Google has it pre-trained models, so where they give the Google News, so they have extracted a lot, humongous amount of data, and from that you can get 300 dimensional vectors and stuff like that. Okay, is it clear?
Yes, sir.
Now you can also use pre-trained models. Probably we'll use pre-trained model when you are using our Navi-based algorithm. What we'll do is, we'll take the Google's pre-trained model, we'll convert each of the emails in this. So now we'll have to convert this. Now we have for each word we have a vector. For each word now we have a vector. Now we need to convert a whole vector out of this for whole email, or for whole sentence, for whole document. Let's say we have this document D1, it contains word 1, word 2, word 3, and so on till, let's suppose, word n it has. Now if I give each word to the Word2Vec, then it will give me an embedding corresponding to that. So each word will have its own embedding, and the embedding can be 100 dimensional, 200 dimensional, 300 dimensional, howsoever you want. Okay, and more the number of dimensions, much richer is the embedding, much better is the embedding. So now how to convert this document into the vector. Now you saw that I have corresponding to a word, I have a vector. Now actually what I want is, I want a vector corresponding to a whole document. So how to do that? So the first technique is basically you take just weighted average of these, you take weighted sum. So you take average of these, not even weighted. So you'll take w1's vector, add w2 vector plus w3 vector, and so on till wn vector, and then you'll divide it by the number of documents. That's one of the simplest technique. So one of the simplest technique is, you will take vector corresponding to w1. So sum over all of wi's, I is from 1 to n. So because each the word has a vector, So take all the vectors, sum it up, and divide by the total number of documents. Okay, you will get an embedding. Is it clear? Is this method clear? So what you will do is, each word has its embedding. So you will just keep on adding all the embeddings of all the words. Then you will divide it by the number. Basically, will average out. Okay, this is one of the embeddings. Otherwise, you can take this is called as average Word2Vec. Okay, average Word2Vec basically means you are taking these words which has embeddings and adding the embeddings of each and every word, then dividing it by the number of documents. Okay, this is called as average Word2Vec. Then we have something called as TF-IDF Word2Vec. Okay, what is that TF-IDF Word2Vec? Now we will not use the weight. You will not use these weights, but rather you will use TF-IDF. Okay, and on top of this, you will also use term frequency and inverse document frequency. So how to use that? We'll see that. So let's suppose you had these documents. Let's suppose now you had this W1, you had W2 till Wn. Each of this has its corresponding corresponding values. Okay, so this basically is a like Word2Vec is d-dimensional vector. So each of these is a d-dimensional vector. So after that, what you will do is you will compute the TF-IDF of each of these W1. So this is W1. You will compute TF-IDF of W1. Okay, and you will compute TF-IDF of W2, and then you will multiply with the Word2Vec. So what I mean by that is, so if I write TF-IDF and Word2Vec, I'll write Word2Vec of, let's suppose, some document 1. So it will be something like this, and you will take term frequency of word 1, let's suppose that's T1, and then you will take this Word2Vec of W1. Okay, this basically can be thought as TF-IDF of word 1. So you will take TF-IDF of word 1 corresponding to review 1, and then you will multiply it with Word2Vec of word 1, then plus term frequency inverse document frequency of word 2 multiplied by Word2Vec of word 2, and so you'll keep on going like this. Is it clear? And then you will divide it by the total number. Basically, you can divide by the total number of these. So you can divide it by T1 plus T2 and so on till T. And here Ti is basically term frequency inverse document frequency of term 1. Is it clear?
Yes, sir.
Yes,
so
sir.
so here you are using TF-IDF, then multiplying it with the Word2Vec. If this let's suppose if this TF-IDF was removed, if this was removed, this is normal average then. Okay. Now if you take TF-IDF into consideration of the Word2Vec, you will make a vector like this. You will make a vector like this, and you will take an average of this. So for each words you had these vectors W1, W2, W3 corresponding to each of the words, and now instead of averaging out, for each word you are multiplying it with TF-IDF value also for the particular document, and you are taking these values over here and you are making an embedding out of that. Okay, so again to summarize this, so we had Word2Vec. So Word2Vec basically what it is, it takes a word and gives an embedding, gives a vector representation. Now in order to create document representation, if you have a whole document, for that we saw average Word2Vec. So how was it working? So here you will take these words, you will take each embedding of the words, add them together. Okay, and let's suppose that is Wi. So this is the embedding. So this is from I to n, and then you will take divided by number of documents. This is the total number of this. And then we had TF-IDF Word2Vec. So in this, the one difference was, now we'll multiply this. We'll multiply T with this Wi and sum over all and summation over all T's. This will be summation over all of this. So now here we'll take TF-IDF, multiply Word2Vec, and then we'll get the embedding. I hope this is clear. So this covers our embedding part. Now we'll use this Word2Vec or TF-IDF average Word2Vec or TF-IDF representation, and then we'll convert our emails into the vector representation, which will feed to our naive Bayes algorithm. Is everybody with me?
Yes, sir.
Yes, sir.
Okay, so I think that we'll start in the next session. This session became, I think, too big. So I hope that you understood this thing. Please go and watch this lecture again if you feel that you haven't understood some of these things. So, and if you have questions, I am willing to take that right now, or you can also ask the questions later.